Okay.
Okay, I need to focus on the looks of those pictures.
Oh my god.
That's what from the fellow you sent me.
Alright, the fundamental theorem of calculus. We've talked about the two major branches of calculus now. Derivatives, or differential calculus, and integrals, or integral calculus. So it's basically derivatives are finding slope, integrals are finding area. Okay, that's the really simplified version of the two branches of calculus. Okay, now there are actually two parts to the fundamental theorem of calculus. We're going to do the first part today and the second part tomorrow. Okay, the second part deals more with this idea. Okay, the connection between derivatives and integrals. And it basically comes down to these being inverse operations. Okay? We'll focus more on that part of it tomorrow. Okay? The part that we're going to focus on today is this down here. Okay? So this you need to write down in your notes. This is not on there. So we can say that a derivative function is a rate. Okay, we've talked a lot about that. And the most common example is velocity. Right? Velocity is the rate at which something is moving or changing position. But any derivative function we think of as a rate function. Okay? If I take the antiderivative, okay, or find the area under the curve, okay, that represents the net change of my original function on that interval. So finding the area under a curve. And we looked at some examples of that before, excuse me. So this down here, okay, this is the fundamental theorem of calculus, part 1. If I want to find the area under a curve, what I do is take the antiderivative. Okay, so here we're saying that capital F is the antiderivative of little f. And then I plug in my upper bound, and I plug in my lower bound, and I subtract them. That will get me the area under the curve. And we'll do plenty of examples of this here in a second. Okay, but star this, highlight it, do whatever you want to in your notes. This is probably the most important thing we're going to do in the second half of the year. And we will use this idea the rest of the year.
Basically, we don't have to do left and right.
If we have a function, yes.
Okay.
So the only time we would have to use LRAM, RRAM, trapezoids is if we have a table. And if we have a table, there's no way of using this idea. But if we have a function, yes, we can use this idea here. So just another way to write this, okay, instead of using capital F and little f, we could just say that, what if I take the antiderivative of some derivative? Right? If I say this is the derivative function, then I take the antiderivative and plug in b and a. Right? So before we do some concrete examples of this, I want to kind of talk about the idea of a rate function. Okay, and we'll talk a lot more about this in the future. Right? Well, I guess a little more notation first. I forgot about this slide. So when we actually do this calculation, and we'll do examples of using this notation here in a second. We actually put in, when we take the antiderivative, okay, we find the antiderivative function, and then we draw a line, and we put those two values, a and b, on that line. So what this says is, I'm going to take this function that we just found, the antiderivative function, and evaluate it from a to b. Okay, that's what drawing a line like that and writing those two values means. Okay, and we'll do a bunch of concrete examples here in a second, but make sure that you have this notation written down. Right? A lot of times students don't put this notation down, okay, with that line, and their notation, they try to make up some notation, and you're just not going to get credit for it on the AP test when you're making up your own notation. All right. So let's just take a look at some word examples here first, where we're not doing any math, okay, and just decipher what each piece of an integral means. Okay, so we're saying we have some function, f of t, and it represents the rate at which your 401k changes in value over 1 month, the month of January. Okay, so first we want to come up with units for each of these pieces. Right, so I'm saying that f of t is the rate. It's a rate function. That means it's going to be something per something. Right, so if I'm saying that f of t is the rate at which your 401k changes, the units of f of t, okay, would be, if we're talking about value, we're talking about change in money per, and I guess they didn't really give us units here, but if we're talking about over the course of 1 month, we're probably looking at it daily, right? So this is going to be the change in money per day. Okay. So if we're thinking about our integral, right? If I'm going from 1 to 31, okay, the days of January, and I'm saying that f of t is the amount of money per day, dt is the rate of change of time. Okay, it's the rate of change of the x-axis, or in this case, the t-axis. So this we say is days. So if I multiply those two things together, if I say money per day times days, what we end up with then, okay, I mean, just thinking about this in terms of fractions, right? Money over day times days. Right, the days would cancel out, and the units of f of t times dt would just be money. So what this is all getting at, okay, is that when I take the integral of a rate function, I just get the total change of something, the net change. So the integral from 1 to 31 of f of t dt would represent the total change in value of the 401k during January. Okay, so if I know that f of t is the rate at which it's changing, and I take the integral of that, that's going to get me the total change in the value of the 401k, okay, the net change. That's what area under a curve always is going to be. It's going to be the net change of that original curve. Okay, so let's try a couple more of these real quick before we try some examples of an actual function. Okay, so here we're saying r of t represents the rate at which your pizza changes temperature in a 475-degree oven 5 minutes after the pizza had been placed in the oven to cook. So if we look at the integral, we're saying we're starting at 5 and ending at 20. So how could I interpret this integral? Okay. The integral from 5 to 20 of r of t dt represents the total change in what? Temperature of the pizza from 5 minutes to 20 minutes. To 20 minutes. Alright. How about one then where we've got two functions? Alright, so in this example, we say we want to see some new music group. A of t represents the rate at which students are arriving at the ticket window. and P of T represents the rate at which they buy their tickets and enter the concert. Okay, so A of T is people getting in line, and P of T is people buying the ticket and going into the concert. So, if I want to integrate A of T from 1 to 5, what is that going to represent? Yeah, the number of people getting in line from 1, so they give us units, we can say, I guess we can just say this is like 1 minute to 5 minutes. So this is number of people getting in line from 1 minute to 5 minutes. Then how about the integral from 1 to 5 of P of T dt? Yeah, the number of tickets purchased from 1 to 5 minutes. And so that would also mean the number of people leaving the line, right? So number of tickets purchased, and then those people leave the line and go into the concert. So we can say number of tickets purchased, which also means number of people leaving the line and entering the concert. All right, so then the next couple of questions, okay, number 3 says, well, if I want to combine these two functions, A of T minus P of T, what would that mean in the context of this problem?
Number of people in line.
So if that would be for number 4, when we're integrating A of T minus P of T. So for number 3, if we're still just talking about those are rate functions, right? Before I integrate, they're still rates. So if I take A of T minus P of T, that's just going to be the rate at which the line is growing or shrinking, the rate at which the length of the line is changing. Right, so we can say the rate at which the length of the line is changing. So if I integrate that rate, if I integrate this, parentheses there, if I integrate this rate at which the length of the line is changing, what would I get?
Number of people in line.
Number of people in line, right? The length of the line, the number of people in line. All right. So one last idea here, and again, we're going to talk a lot more about this idea relating position, velocity, and acceleration in another lesson, but just to get this ball rolling here. Okay, we know velocity is the velocity is where positive direction is to the right. So velocity is the rate at which what is changing? So position. Right? Velocity is the rate at which position is changing.
Oh, I remembered something.
Okay. So speed is the absolute value of velocity. So that doesn't have anything to do with one changing at the rate at which the other is changing. Okay. Velocity is the rate at which position is changing. So if I take some velocity curve and I integrate it from 5 to 50, that would be the total change in position from 5 to 50, right? Whatever those units are. Could be minutes, could be hours, could be days. Total change in position from 5 to 50.
Oh no. I rate conditions.
Okay, now this, we've touched on this term already when we did derivatives with position, velocity, and acceleration. Okay, this special term, okay, the total change in position is called displacement. Right? So acceleration then is the rate at which what is changing? Velocity. Right? Since acceleration is the derivative of velocity, that's the rate at which velocity is changing. Right? So we'll spend a lot more time looking at problems that deal with this idea in the future. Okay, but we'll skip that. For now, let's use the fundamental theorem of calculus. So our fundamental theorem of calculus was this, right? The integral from a to b of f of x dx is equal to f of b minus f of a. So let's use that here to solve some of these integrals, right? We've never solved anything like the area under the x cubed curve. Okay, everything we've done has been able to be done geometrically. Right? We've used trapezoids and triangles and circles to find exact areas, but now we can use the fundamental theorem to solve this. First step is to take the antiderivative. What's the antiderivative of x cubed? 1/4 x to the 4th. So the notation then, okay, once we take the antiderivative, that's where I use this bar, okay, and put my bounds like that. Okay, so I've taken the antiderivative, and then I put this line, or this bar here, and just rewrite my bounds. So what this says is I'm going to evaluate 1/4 x to the 4th between 1 and 3. So then to use this idea, right, I'm going to plug in my upper bound into this function. So I'm going to plug in 3. So I'm going to say 1/4 times 3 to the 4th. That's my f of b, okay, my f of my upper bound. And then I'm going to subtract, I plug in my lower bound. So I'll have 1/4 times 1 to the 4th power. So what is 1/4 times 3 to the 4th? Right. 3 to the 4th is 81. So this would be just 81 fourths. And then this would be 1/4. Right? So minus 1/4. It's 80 fourths, which is 20. So the exact area under x cubed between x equals 1 and x equals 3 is 20. So yeah, when we're doing definite integrals, okay, definite integrals means we have bounds. We don't care about plus c. Indefinite integrals, whenever we don't have bounds, are the only times we would add a plus c. Any other questions so far?
Okay.
Alright, let's do another one together. Okay, so on this one, first step, find the antiderivative. So what's my antiderivative here? 1/3 x cubed minus 3x. I want to evaluate that from 1 to 2. So I need to plug in 2 into the entire function, right? One thing that the students sometimes mess up is they'll plug in 2 into this first term and then 1 into the second term. That's not what we want to do. Right? We want to plug 2 into the entire function. So I would have 1/3 times 2 cubed minus 3 times 2. Okay, that's my f of b. Then I'm going to subtract, plugging 1 into the entire function. So minus 1/3 times 1 cubed minus 3 times 1. And so 2 cubed is 8, so this would be 8/3 minus 6 minus 1/3 minus 3. So I can get some common denominators here. So this would be 8/3 minus 18/3 minus 1/3 minus 9/3. So negative 10/3 minus negative 8/3. So negative 10/3 minus a negative 8/3 would be negative 2/3. So the exact area under x squared minus 3 from 1 to 2 is negative 2/3. How do we feel? Do we want to do any more together, or do you guys want to try some of these on your own? Maybe. All right, so we've got 20 minutes left.